Hello everyone, my name is Konstantin Vladimirov and welcome to the 11th lecture of the master's course in C++ at MIPT. Last time we descended deep into what I like to call the cave of wonders, the strange and magical realm of constant evaluation in C++. We talked about Constexpr, Consteval, compile time objects, compile time pointers, the rules of the cave, the djinn who guards the treasure, and the many surprises waiting behind every corner. Today we're going to dive even deeper. We'll revisit constant evaluation from a more powerful angle connected to modern metaprogramming and see how compile time techniques evolve in C++20, C++23, and even the upcoming C++26. So let's get started. And let's begin with a puzzle. A very old puzzle. It's attributed to John von Neumann himself. You have a balanced scale and you have some number of whites. You can put whites on either pen. To white something, like to white a rabbit, simply means bring the scale into balance. For example, if a rabbit weighs 4 kilograms, you can balance it using whites 3 and 1. Or you can balance it using whites 5 and 1. 3 and 1 here and rabbit here, or 5 here, rabbit, and 1 kilogram here. And the challenge is, what is the minimal number of whites needed to weight every integer from 1 to 40, like 40 kilogram rabbit also. Now, we all know the easy upper bound, binary numbers. Whites of 1, 2, 4, 8, 16, 32, 6 whites easily cover all numbers up to 40. But this is true if we are using only one pen for whites and other pen exclusively for rabbits. If we can use both pens, can we do better than 6? Can we do it with 5, with 4? And it turned out we can. And please pause the video now and try to solve this simple puzzle. 3, 2, 1. And solution, of course, is a balanced numeral system, specifically the balanced ternary system. Its digits are not 0, 1, and 2, but -1, 0, and 1. But the system is ternary. We'll write -1 using the symbol j. So 1, 0, j is 8, because -1 times 1, 0 times 3, and 1 times 9. And -1, 0, 1 is -8. And now, how do you think? 1, 1, -1, 0, dot, -1, -1. What is it? This is like simple decimal dot, like 1.2, yes. And it's a bit more exotic, but let's try to decode it. And we will do it in the moment, you will do it in the moment. And now, with this system, you only need whites 1, 3, 9, and 27. And you may convince yourself that this is enough. For a bit like of 19 kilogram, yes? What is 19 in this system? And in this system, 19 is something like 27 minus 9 plus maybe 1. And to weight a rabbit of 19 kilograms, you put 27 and 1 on one pan, and rabbit and 3 on another pan, and this is -3. And 4 whites total, only 4 whites, and you can write anything from 1 to 40. And let's explore the properties a bit more, but now please pause the video again, and to show me you understand this, please guess what it is. What is decimal number here? How to convert this from treats to decimals? 3, 2, 1. Okay, I believe you did it. This is 32 and 5 to 9. And basically, treats have several fascinating properties. First of all, negation is trivial. Just swap everyone with j and vice versa, and you will have a negated number. This is the example. And the fractional ones also work out nicely because dropping fractional part always rounds to the nearest integer. Like dropping here, fractional part in decimal system will round not to the nearest, because nearest here is 33, but dropping decimal part here in treat system rounds to exactly 33. And Donald Knuth, of course, wrote about it because, like, balanced ternary has a lot of charm, and books of Donald Knuth are charming, and you can look it up in TauCP. But I'm not telling you this because I want you to become a balanced ternary mathematicians. We are here for one thing. We want to use treats in our C++ programs. So let's move toward that. And what we really want is basically this. This is a suffix. We talked about this last time. And we want this to work like this. We want this to output like 8 and -8. And this shall be clean, elegant, and see this Constexpr compile time. And we could use a user-defined literal that directly returns an int and do parsing inside it. And then this suffix will just return an int. But that would lose many nice properties. It becomes just runtime parsing. What we actually want is an object that stores the treat digits. And this object shall live in compile time and be compile time convertible to integer. So let's build such a type. Here's the idea. We make a class ctTreat that stores the digits internally. But before parsing this string, we don't know how many digits to store. The user gives us a string literal of arbitrary length. Could we store them in std array? Not really, because the size is unknown. Could we cheat with an oversized array? Sure. And Jason Turner calls the oversized array trick, but it's ugly. The clean modern solution is use std vector of int inside a Consteval constructor. And because this constructor is Consteval, this object can live only inside the cave, only in compile time. And so this std vector is perfectly fine. All memory will be deallocated in destructor of this Consteval object. The constructor itself can only run at compile time. The vector allocation happens inside the Cave of Wonders, and we don't have to worry about runtime memory. And the constructor simply parses the characters 0, 1, and j, and gives us a proper compile time object with vector of digits, representing the treat number. And the next step is conversion. And now that we have the digits stored, we want this to work. So we define a Constable conversion operator to int, sorry for this, or to any integral type, and it simply accumulates the digits for each digit d. And one detail, notice, this operator is Constable and const. And the const matters. Even at compile time, only const methods may be invoked on a const object. And now we have a fully functional compile time number object. All we need is a literal suffix, which is really simple in this case. And here it is. A literal operator returning a compile time object. It is OTA. It constructs CT-treat inside. And now 10j underscore treat is a CT-treat object, which can be implicitly converted to int or to any other integral-like type. Yes, this is t equals int by default, but we can specify any other type here. And this is exactly what we want. This becomes an 8, this becomes a -8. Beautiful. And with that, we built a fully compile time balanced ternary numeral system inside C++. Isn't it great? Okay, let's go ahead. And here's another place where Constable turns out to be extremely powerful. Sometimes we want operators that make sense only in a compile time context. A perfect example is bitmask operation, this one, used inside a switch. Usually you can't write like this, bitmask or bitmask, because the expression b0 or b1 is not a constant expression unless the compiler can evaluate it on the spot. But if we define the bitwise OR operator as constable, then the compiler is forced to compute the result during constant evaluation, which means the expression does become a valid case label, and suddenly everything works exactly the way you always wished it work. This is a surprisingly elegant use case. Compile time only operators whose whole purpose is to make the syntax nicer and safer in places where runtime evaluation simply isn't allowed. And here, no runtime evaluation, of course, in case statement, no runtime evaluation allowed. And then we are using constable operator again. And note, this operator was also constable because this class have constable constructor, and Constexpr here just will not work. Okay, and let's dive into some C++26 material. And the first feature I want to show you is something I personally love and waiting for it in C++26. Even though we still don't have the final standard, I'm really expecting it. And it is template 4. And template 4 is like a counterpart for the Constexpr if. So naturally, now, before like C++26, the language do have compile time 4 and don't have compile time looped. Template 4 bridges this gap. And think of it as a way to iterate over things that are known at compile time without resorting to template recursion or pack expansion tricks. The simplest use case, like here, is to iterate over a parameter pack. The print all example you see on the slide iterates over its pack here, and for any for any t, just prints this t at runtime. This template 4 iterates at compile time, but this print occurs at runtime, and this is perfectly okay. But someone usually asks, okay, we can iterate with template 4 on parameter pack, but can we iterate over all values of an enum? And that's where the new C++ reflection machinery comes in. And to iterate over an enum, we need to cross a boundary from the ordinary world of runtime C++ into the meta world of compile time reflection. And the operator that does this is what the community calls ears operator, like ears, you see. But I would I would call it Catgirl operator because I mean ears like cat ears, yes, and Catgirls are nice. And I didn't invent this terminology, and I really like it. You may call it ears operator if you don't like Catgirls. I think you do. And this one, ears int, reflects, it gives you a meta value, a compile time reflection object R that represents this type, this int. And once you're in the meta world, you can query it. Like here, this meta object Catgirl of bitmask or ears bitmasks gives you a meta value, and you can query enumerators of stud meta enumerators of for this meta value, and compiler will happily like give you all enumerators, and only first is of interest to me, like b0, and e now is a meta value of enumerator b0, and for this enumerator I can have stud meta identifier of it. And you can query it, you can get its enumerators, get their identifiers, and then we can inject them back into ordinary C++ using splicers. And splicers are those square brackets with colon. If you pause the video now and read this code slowly, and I expect you will do it, you will see the following: reflect bitmask, fetch an enumerator, get its textual name, splice it back into real C++ as a value, is S1, and print first textual name and then value. This round trip is the basic pattern of the C++26 reflection. And let's remember, those constructs are called splicers. It is like square brackets and square bracket and then a colon, square bracket colon and colon right bracket. And those splicers allow you to bring a compile time meta value back into ordinary C++ syntax. You can splice types. This is reflected long. This is meta value of long. This is reflected int. This is meta value of int. I am calculating in compile time some condition, and then I'm splicing back the resulting type, either long or int. And you can splice indices, which makes it trivial to re-implement like tuple element function from the standard, like meta functions, tuple element meta function from the standard. Using reflection. First, we are gathering meta array of all element types, and then splice the one we want, indexing in the compile time by the compile time evaluated index, which is a template parameter, which is a compile time object. And the amount of template machinery this removes is enormous. And it's the first time the language gives us a real compile time introspection. And yes, I'm waiting for it a lot. But even now, compilers with some of proof of concept implementations are available, and Clang with a reflection branch is available for you. And we can even like try and fail on some problems and so on. So let's see how this plays together with Jeans, Catgirls, and the Cave of Wonders, because the Cave of Wonders is like somehow empty without Catgirls. And now let's try something natural and very tempting. Iterates over all enumerators of bitmask with the template 4 in runtime and print their names. This probably should work. It's exactly why template 4 exists, but it doesn't work. And let's see on the Godbolt what is the diagnostic for this. And let me show you the compiler explorer. And here we are. Let me press F11. My audience loves F11. Okay, so this should work like for template 4. This is like for auto for enumerators of bit mask and then just print. But this doesn't work. And what is an error message? And an error message is strange. A range must be initialized by a constant expression. Could not compute size of expansion. Something like this. What's happening? And if you will read the diagnostic carefully, it's quite revealing. What the compiler is complaining about is that the range expression inside a template is not a constant expression. You see, the begin here is like from begin to end, yes? And the begin here contains an enumerator of, like stealing them from the Cave of Wonders. Because those enumerators are of dynamical size in this implementation. And this dynamical size just cannot be put into the runtime context. And template 4 is like runtime context because we need to access this E in the runtime to print it. And this is the problem. And how would we solve it? And I think now you know enough. Just go read some documentation and figure out how you will solve it, how you will print all identifiers, so all values and so on. And if you did it, is great. If you just want to enjoy the show, let me show you the cat girl in the Cave of Wonders. And this is happy cat girl. So what we do? We need a container that exists both in compile time length and runtime length. A legitimate bug we can view inside the Cave of Wonders and safely carry out. And we cannot do it with vector. It has the dynamically allocated space. But we have our stud array. So here is the trick. Enter the cave with Consteval function. Obtain the list of enumerators while still inside the cave. Extract their identifiers. We can now calculate the size of these enumerators and make stud array of this size, because this is legitimate constant expression syntactically. And now, once we stored them into the stud array and filled our bag with treasure, we can return it from the Cave of Wonders to the real world. And once array is returned, we are already outside the cave, and our treasures, the names of the enumerators, are now perfectly legal to iterate over in a normal for loop, or in template for loop, or everything else, yes? And this technique, using a value-based container as a smuggling bag, shows up a lot when working with C++ reflection. It's a beautiful way to reconcile the two worlds without violating the genius rules. Okay, and before we move on, I want to show you a small case study, partly to demonstrate the power of reflection and partly to show its poverty. The problem is deceptively simple. Given a type T, determine whether it is an object type, whether it can be an object type. And you probably remember from the type system lecture, an object type in C++ is any type that can actually have an object, which immediately includes void never an object type. References also never object types, because reference is never object. Functions not object types, but pointers are object types, arrays are object types, pointers to functions are object types, and recursively so. Say references to functions are still not object types, or references to pointers to functions, or functions returning references to pointer to functions, taking an array and returning a reference to pointer to functions. So we get this pattern on the slide. Some types are object types, some absolutely are not, and some are dangerously counterintuitive. Now, what I want is to print a table like this automatically. I don't want to handwrite this and tries. I want to feed a type into a helper and get a one-line answer. How would you do it in old good C++? Like in C++20. Please pause the video now and try to figure out simplest solution, no metaprogramming, just some macro substitution, to print this on the screen for any type given, like for int pointer print this, for void print this, and so on. 3, 2, 1. And solution without Catgirls is really boring. But before reflection existed, this was the best solution I had. It worked. We can evaluate stud is object, and this is good part. To print either is object type or is not an object type. And the tricky part is printing name of the type. And as I always tell my students, C++ macros are only sane in two situations: stringification and token concatenation. And this is exactly one of those rare legitimate cases. The macro #t stringifies the name of the type, so we can print intref or int pointer to function or so on, exactly as free. It's ugly, but it gets the job done. It gets the job done. And what about reflection? Once we have reflection, we can finally get rid of any macros. We have dump status as a simple function. We still evaluate stud is object of t the same way, but instead of relying on the preprocessor to stringify the type name, we can ask the compiler directly, please give me the display string for this type. And that's what stud method display string of is supposed to do. It gives you a textual representation of the type, generated entirely by the compiler with no macros. And now dump status of t becomes a normal function template, no preprocessor tricks, no stringification, no duplicated code. This is where you start feeling the real promise of reflection. We can finally manipulate everything as values, print types, inspect enumerators, reason about everything without going through the ancient machinery of macros and template metaprogramming. And there is one coach though. Let me show you on the Godbout. In this case, you can see everything is fine, and this is fine, dump status is fine, and everything compiled, but this just not working. Let me show. It prints everything good, but for some types, it prints like simply function type or function pointer type. You see, types do not have identifiers. We cannot use identifier. And display string works for types, and it is not perfect. In some cases, it devolves into generic function type placeholders. And that's a sign that the reflection prototype is not fully implemented yet. But even with those limitations, this is vastly cleaner than the macro section. So let's ask the big question of today. Does Constexpr actually add anything to Metaprogramming? reflection obviously does. That's the big hammer of C++26. But what about plain old Constexpr? The thing we got back in like 2011. Does it change how we write metaprograms? And the answer is yes, dramatically. And to see why, we are going to revisit one of the metaprogramming examples from my final lecture and rewrite it entirely with Constexpr without touching Boost.Hana. And to do that, I first need to introduce a surprisingly powerful concept of index sequence. This is, to my mind, one of the most underrated tools in the entire standard library. And this is an integer sequence. And sorry for this. What is an integer sequence? An integer sequence is basically a type parameter followed by a pack of integral constants. So, integer sequence size t1, 2, 3. Yes, it is like this class that holds type and constants of this type. And when the list is made of size t's, we call it index sequence. And there is also std_make index sequence of n, and this is where the magic happens, because if you write std_make index sequence of 3, its type becomes exactly this. Its type becomes index sequence of 1, 2, 3, or, which is the same, integer sequence of size t1, 2, 3. And let us carry around compile time lists of integers as actual types. And this becomes a foundation for all sorts of compile time mapping tricks. Let me connect this back to the MPL example from the final lecture. I hope you still remember it. If not, please go revisit it. We had a compile time list of fixed protocol tags stored in an MPL vector. Now we can store the exact same list using just integer sequence. This type is now a list, and inside our fixed message wrapper, we can write something like fixed message dot get tag entity of 11, meaning please find the tag with identifier 11 in the compile type list. So replacing MPL with integer sequence is not only possible, it's natural and far simple. Let me go through some details on the code note. And here we are. Yes, so what can we see here? We can see this targeted structure, which is exactly the same. And we are keeping those structures, and we can get and operate on them at runtime. Fixed message, get tag entity of 11, and only indices which are possible are 11, 35, and so on. And how do we do it with MPL? And with MPL, this solution we already seen, we have this comment tags count equals MPL size type value. We have MPL find, and this value is real index value, because when we are finding this tag inside the tag list, we are taking its position, and its position is just position inside an array, built-in array or std array. In this case, it is std array, and this is how this works. This is how this works in MPL. But let's rewrite it using Constext. How will we start? First, get tag entity. And to make this work, we need a bridge between compile time and write time, and we want a normal member function, not a Constexpr constructor. They can still use compile time logic internally. And so inside get tag entity of tag, we construct a Constexpr helper object, a little list of integers built from the index sequence. And then we ask that helper to locate the index of tag dot fact. Okay. And what is .find? We need this Constexpr find function for that list, and that's on the next slide. And this is list like ctins. This Constexpr structure with Constexpr constructor holds an array of integers and provides a Constexpr find that linearly scans it. Of course, it would be much simpler with just template 4, but presume we don't have template 4. And then we are just scanning the integer sequence. We are getting it into the stud array, and we are just iterating over the stud array. It's not recursive template magic. It's just ordinary control flow. And this is exactly the point. Constexpr allows us to replace template metaprogramming with pretty normal code. No Boost.MPL, no type gymnastics, just a small array and a loop. And this version is easier to read, faster to compile, and still computed entirely at compile time, and still results are usable at runtime. And now let's do something slightly more interesting. Let's rebuild our make integer seconds with reflection, just to experiment with our reflection possibilities from C++26. We reflect the template arguments as meta values, push reflected constants into a meta vector of this size. Of this size. First element of meta vector is t, and every next element of meta vector is increasing constant. And then call substitute to construct a new integer sequence with exactly those reflect values. This substitute is a new meta function we haven't used. So what are we doing here? We do have stud vector with first argument is meta value of t, and other arguments are meta values of 0, 1, and so from 0 to n. And do you see this is the same like type? This type is meta value, and meta value of t is the same type that is meta value of 0, meta value of 1, and so on. And then all this vector, all this args vector, we can substitute to meta value of stud integer sequence type. And when we are substituting this to this type, we are getting this meta value on the return. And returned meta value is all this meta vector substituted with this meta integer sequence. And then here with splicers, we are injecting it back into ordinary C++. And this is the purest form of compile time metaprogramming in C++26. A fusion of concept reflection, technical construction with absolutely zero template rehash. And yes, this example is a bit of flex, but I wanted you to see just how much expressive power the language gives us once we have like ears and splicers. And because now something like make index sequence becomes just normal imperative logic, just another loop. Okay, let's return to Metaprogramming. So at this point, you've seen quite a few different metaprogramming techniques. Old school template tricks, MPL style computations, fusion style computation, Constexpr based algorithms, now full-blown reflection with Catgirls and splicers. And this raises an interesting question. With such a large toolbox, how do we choose which technique to use? To explore that, let me show you a little puzzle I recently used in my Telegram channel, a real-world flavored example that demonstrates how differently the same problem can be solved depending on which style you pick. And here's the setup. you have a bunch of template specializations of function foo. And maybe for int return 2 and for float returns 4, and the primary template returns 1, and then you have a function Sumfoos that just does a fold expression, this one. Now the task is write the function, apply Sumfoos that takes a tuple, extracts its types, and calls Sumfoos with those types. So if the tuple is tuple of int and float, you would apply Sumfoos to call Sumfoos of int and float. So if this is int and float, this pack shall be pack of int and float. And this is something we all do all the time, unpack types from a tuple and feed them into a template. But instead of showing you only one solution, I want to show you 3 completely different ones. So now, please pause the video and try to figure out your solution, your way out of these bots. And Bibliography did it. 3, 2, 1. Okay. So, standard section. Let's begin with classic answer. Before C++26, the conventional way to attack a tuples type list is to use a helper struct like this. We do have this argsupplier specialized for tuple of args, and these are args. Down, unpacked with partial specialization. And inside these specializations, we can use this pack, and we are using it. Okay, and then apply Sumfoos just instantiates this specialization of argsupplier and call static apply function, and probably even decal type of filter will be better here. But I hope you can add all forward logic, all decal type of filter, and so on, because we already talked about this in our lectures course. I just making code more compact for slides. Okay, nothing fancy, but it works everywhere. And with reflection, of course, it is just substitute. The idea is take Sumfoos, convert it to meta function using the Catgirls operator, extract the template alphabets of tuple using reflection, use substitute to apply those elements to Sumfoos, splice the whole thing back into normal C++ and call it. Here's call right. In other words, reflect the function, reflect the tuple, substitute template parameters, splice scope. This is metaprogramming on easy mode. No template gymnastics, just manipulating meta values like ordinary options. It's elegant, compact, and perhaps slightly terrifying, but it is C++36. And now let me show you something in the middle of this, like reflection here and old school way here, but what is on the halfway? And it is very important. On the halfway, there is a Consteval solution. Consteval solution uses no reflection at all, but only pure Consteval. This solution is extremely instructive because it demonstrates something subtle. A Constexpr function itself, like this Consteval instance function, can serve as a pure compile time type carrier. Here's the idea. You declare a Consteval T instance with no body. This function can never be called. Its purpose is to produce a type-dependent expression that survives into depth. And you declare a helper container of T that has static method test calling Sumfoos of T, this helper. Okay, and then you create a value function template that given something like an instance of tuple that uses a pack T and returns a container of T. And this is value function. Taking this tuple returns the container of T. And finally, inside apply Sumfoos. You're right, inside unevaluated context, call of value function which is without body, but it is not a problem for unevaluated context. We can unevaluate everything even without body. Value of instance of tuple, like call here and call there, and then container of t helper. Now have this function test that you can call. This is very similar to depoval, except that it works entirely at compile time without even instantiating an object. It just varies the type information through the type system. This approach is a kind of metaprogramming aikido, no partial specialization, just steering the type system in the right direction. Please try to understand this example because it is very instructive and it have interesting consequences. If it's comfortable to you, pause the video now and try to understand it before you can. Okay, let's go ahead. Here is the key observation. A constable function can act as a compile time type holder. You don't call it, you don't evaluate it. You only use it inside deco type to produce the specific type you want the compiler to see. It's a beautifully simple pattern and one that becomes incredibly powerful when combined with techniques like the one we just used. Let's look at classic metaprogramming problem, one that Björn Strostrup himself proposed decades ago as the canonical example of why static type systems matter. The challenge is to model physical quantities, things like meters, seconds, meters per second, in such a way that dimensional analysis happens at compile time. So we write code like this code on the slide, and the compiler should catch dimensional mistakes instantly. How do we achieve it? The key idea is beautifully simple. Let's represent each unit as a tab. This is unit. Specifically as a tab that stores its exponents, meters, kilograms, seconds, etc. For instance, unit of 100 means meters, unit of 001 means seconds, 10 - 1 means meters per second, so on. And this is pure type level bookkeeping, but exactly the kind Bjarne envisioned as the essence of the early Metaprogramming in C++. And once we have a type that represents the unit and physical quantity is just a number, this double, and the unit type as a template parameter. It is like in physics. Numbers exist. Dimensionality is our fantasies. Dimensionality is template parameter. And that's it. Unit of 100 is matter. Value of unit 10 - 1 is speed. Value of 10 - 2 is acceleration. The compiler now treats value of matter and value of second, and basically two doubles. Value of matter is basically double. Value of second is basically double. But compiler now treats value of matter and value of seconds as completely different types, which is exactly what we want. This lets us encode dimensional correctness directly into the type system. Of course, we add user-defined literals so that writing code is pleasant. By the way, this space is not allowed anymore. Please use like quotes and then underscore. And each literal, like meters, seconds, seconds to square, simply constructs the appropriate value of appropriate u. So syntactically, we get a very clear interface, but underneath, we are still manipulating type that encode the unit's dimension vector. And that sets the stage of the interesting part, arithmetics of quantities. Let's try to write multiplication. Conceptually, it's trivial. Meters times meters is square meters. Meters times seconds is meters times seconds, and so on. And mathematically, we just add the exponents of units. So we need to multiply values, and here we need pairwise add exponents. The result is unit of L1 plus L2, M1 plus L2, T1 plus T2, and corresponding values. In C++ terms, that means we need to inspect the exponent inside each unit type, add them component-wise, and immediately type that represent the product Q. And that is exactly where metaprogramming comes in, because we are performing unit algebra at compile time. Later, now we have template forward, reflection, Catgirls, and splices. We can solve this in extremely elegant ways. But even without modern tools, this example is a perfect illustration of why compiler computation is so powerful. A compiler becomes your dimensional analysis engine for free. And now let's move from classical template metaprogramming to something much more modern and elegant, Boost.Hana. Hana was born around 213, I believe, and its fundamental idea is very beautiful. Treat types as values. Oh, we just heard. Yes. Treat types as values and make type level computation look like ordinary functional programming. Hana essentially unifies what I earlier called quadrants 3 and 4, type transformations and mixed computations. The code abstraction is a tiny wrapper type which carries this T. And this wrapper lets you manipulate types as if they were first-class objects. And from that point on, like add pointer of type T is type of T pointer. Yes, it is like manipulating an object. And from that point on, compile time algorithms become incredibly expressive and almost real. Before Hana, we often relied on fairly grotesque spinner tricks test properties like are these two types the same. With Hana, this becomes a real overload resolution problem. And the whole language C++ is about overload resolution. You see, we sacrificed Huey Milner for overload resolution, and now we are using it. We are enjoying it. And we overload operator equality for type of T and type of U. And if T and U are different, we are returning false type. And if they are the same, we return true type. That's it. Now what to you? Though let's hope substitution fails in the right direction. Just normal overload resolution, which is exactly what language was designed to do. This is not spinner abuse. This is spinner. This is definitely spinner. Either this or this wins, yes, but this is spinner used correct. And let me remind you how things looked in Boost.MPL. MPL performs computation on types themselves. Let me remind you how things looked in Boost.MPL. MPL performs computation on types themselves. You build a type level vector of int, boolean, char, and so on. You build the we call MPL remove if with some type predicate like stud is void, and MPL synthesizes a new type like this list without void, yes, and it works, but the syntax is heavy and everything happens through template metaprogramming machinery. Hana's approach is much closer to normal programming. You build a tuple of type objects, Hana tuple T, and then you call Hana remove if, which is a Constexpr function on this Hana tuple with this Hana trait, which is really similar to stud is void, and actually it calls stud is void under the hood. And type level code in Boost.Hana approach, in Constexpr approach in general, stops looking like a stretched parallel universe. It starts looking like the ordinary functional code that happens to run inside the compiler. And previously with Boost Fusion, and here is Fusion example, we could mix values and tag level predicates, but it still felt quite specialized. Fusion tuples, MPL lambdas, meta function placeholders. HANA eliminates this complexity. In HANA, a tuple with runtime values is just a tuple. Types themselves are also values wrapped in type T. So you can write HANA remove if lambda, and this is normal lambda, no magic here. That returning HANA traces floating point of HANA type ID of this element. And this element is wrapped in type T. And this is mixed computation. You are like deducing this type and you are computing this value. This element is just runtime value. You are you're computing values in runtime, and you're computing new list in runtime. And in runtime, new list will be this list with all removed floating point, list of 1 and hello. Okay. In other words, HANA collapses is a mental boundary between compile time data and runtime data. It treats them with the same conceptual tools. And now let's revisit our physical quantity example, but this time using HANA. Instead of representing a unit as like our own unit class of meters, kilograms, seconds, we can represent it as HANA tuple of integers, like tuple C, compile time tuple of integers. And this is really akin to index segments, I believe, yes. And there's meters, there's seconds, and so on. And there's seconds to the square. And this is already a compile time value. And our actually value of unit wrapper barely changes. It simply holds a double. What matters is that the unit type is now discoverable, iterable, and combinable through HANA's algorithms. And here's the punchline. The hardest part of original exercise, combining units by adding exponents, now becomes trivial. We just use HANA zquiz 2 plus d1, d2, which doing exactly this. It takes both unit parameter boxes compile time tuples of integers, and this walks over them element-wise and adds corresponding components. It produces a new HANA tuple representing the resulting unit. We wrap it back into value and multiplication is done. This is exactly what Bjarne Stroustrup, I sure, is exactly what Bjarne Stroustrup wanted 30 years ago, but expressed in idiomatically model C++ style. Instead of template recursion and meta functions, we're simply using higher order function. The moment you need type level arithmetic, HANA makes it feel as natural as manipulating regular lists and vets. Okay, and now the final homework of this video. Yes, this really is the last one. A month from now we'll be well into the exam season, and I'm not giving any beyond to this. So here is homework 8.3. You must, and I want to remember, I want to remind you, you may write solution here in the YouTube comments. I don't see a lot of solution comments of this course. Okay, you must solve the multiplication problem for physical quantities without using any metaprogramming libraries. No HANA, no MPL, no Fusion, no meta reflection unless you really want to prove something. Just write plain C++ like the elders did. Take 2 units, add their exponents, and synthesize the resulting unit type, and that's it. It's not as scary as it looks. One done the example from lecture, the classical unit of meters, kilograms. Second structure, the multiplication almost writes itself, And if you end up reinventing a tiny metaprogramming utility, I would be wonderful. That's part of the exercise. If you can do it with reflection and make it build on Godbolt, I'll be genuinely happy. But that's all. And the second task, this one is a bit of mini Olympiad. Your input is a tuple of types. I'm intentionally not specifying which tuple. It doesn't have to be stud tuple. You can invent your own as long as it can hold a pack of types in some form. Your job is to return the same list of types but sorted by increasing size. So from int char long, you must produce like char int long. Two important constraints. First, the sort must be stable. If two types have the same size of, they must stay in the same relative order. Second, every student might use a different metaprogramming idea. The first person who submits a solution with a particular library claims this approach and removes it from the pool. First HANA solution blocks other HANA solutions. First Fusion solutions block other Fusion solutions. First reflection-based solution blocks all reflection-based solutions. So originality is part of assignment. It's a fun one, and honestly, I'm using 4 points if you're fast. And I wanted to run this block with a small friendly competition, just like in the first course. Okay, and finally, let's briefly talk about the bibliography. This is the end of the Constexpr module, so I selected a set of talks that really shape the way modern C++ thinks about compile-time property. First, of course, is the classic talk by Jason Turner and Ben Dean, Constexpr All the Things. This is the talk that effectively kicked off the whole Constexprization of the assembly library. Historically, it was the moment when the Constexpr stopped being a strange experimental feature and started becoming a structural part of the language. The second terminal talk, Consteval, All the Things, is much more reflective and cautious presentations. Just some thinking out loud about where Consteval really works and where it becomes overkill. The talk is excellent, but I'll be honest with you, the first 40 minutes are boring. You just have to sit through that. But once the second half begins, the real fun starts, and it absolutely pays off. However, it would be strange to limit ourselves to total alone. So here are two more that I strongly recommended. Dietmar Kuhl, Constant Fun. A wonderful talk. Kuhl is the person who effectively introduced the idea of Constexpr as an UB sanitizer, if you remember. It was previous lecture. And remember how we talked about Consteval catching undefined behavior more reliable as a Clanketider sanitizers? That's where this whole line of thought comes from. And Rainer Grimm, very clear, very structured talk, back to the basics constant Constexpr. Unfortunately, Rainer passed away quite recently. And this talk remains one of the best primers on model constant evaluation. And finally, I could not include this one, David van der Voort, Gazing Beyond Reflection in C++ 26. Van der Voort is a legend, the primary author of the big foundational metaprogramming MOOC with Nicolas uses. And Van der Voort doesn't give talks often, but if he comes out with something, it's always worth watching. This particular talk covers exactly the tools we used today in the metaprogramming, the Catgirls operator, the splicers, and the whole design flows with behind reflection in C++ 26. It's dense, but incredibly useful. And that's all for today. Thank you.